Indexes are important. Let's dive into the internals next on Tales from the Field.
Some food in you. Step 3, think real hard about what you want to be. Step 4, everybody just do your thing.
Wake up, today's gonna be a good day.
If this is your first time finding your way over to Tales from the Field, give us a like and give us a subscribe. We have our community roundtable every Tuesday at 1 p.m. Eastern Time, live, but you can catch the recordings on our YouTube channel at any point in time. On Wednesdays, we drop our MS Tech Bits. That's one of those videos that you're watching right now. Okay, let's get on to the content. All right, we're going to start with creating our database for these demos. We're going to call it demo indexes. We'll do a quick refresh in SSMS. Boom, there's our database. So let's scroll down and let's go to our first one. What we're going to do is we're going to create a very small clustered index. Keep in mind, we've got a primary key. That's a constraint, not an index type. And we're going to just insert 2 records. Why 2? Because even though this is a clustered index, it is so small, we're not going to start out with a root page. You can see that we've got 2 pages. One of them is my IAM page, page type 10, and then I've got my page type 1. Page type 1 is my data page. Page type 10 is the IAM page, the index allocation map. So if I come in here and I insert 1 value, I'm just going to insert some default values, you're going to see that we get 2 pages allocated. The reason is we get our root, a page type 2 page, and then we also have our leaf level, our data, because we didn't have enough room on that previous page to be able to store all the data. So we get a new page, page 474, which is a type 1 data page. And now we've got essentially 4 pages to our table, our IAM, our root, and our 2 data pages. So one of the things that I want to do is let's take a little bit closer look at this root level page. So what I'm going to do is let's go back and let's grab page 473. We're going to do a DBCC page. We have to turn on trace flag 3604. So that way we can get a friendly output. And you see, here's our friendly output. I've got my page ID. That is the root level page, the row level 0 and 1. My levels, my child, and there's my individual child pages and the low key value. The low key value is null because it's a throwback, because an integer value can also be negative. I started at 1, and so it's reserving the space for if I were to put a negative value in place, because we can go to negative billions. So what I'm going to do is just show that we've got a low value. I'm going to insert 3 records. That should, because we can get 2 per page. We've already got 3. That should cause us to get another additional page. So if I come back and look, I can see we now have page 475, and we have my ID key. The low value is 5. That's incremented. So another important concept is that when we rebuild an index, we're going to get all new pages. It's a little bit like moving an apartment. I've got to maintain my old structure and my new structure, but I'm getting something completely new, and this is a fully logged operation. So when you have those overnight indexing jobs running and you see your log file grow a lot, that's because you're getting allocated all new pages, IAM, data pages, root level pages. So now let's play around a little bit with the heap, because we've talked a bit about heaps and we need to understand them versus our clustered indexes. So we're going to create essentially the same table structure with the same default values. But what we're going to do is we're going to not have a primary key constraint or a clustered index on it. So we're going to be doing a pure heap. We're going to insert 15,000 rows into this table, and it'll take a minute or 2 to be able to do that. But once we get this data in there, we should also have essentially 2 rows that we can store per page, but we should have a decent number of pages that we've actually created within this heap table. All right, there's our affected rows. So now that we've got our heap table, the first thing I'm going to do is drop clean buffers. It's going to drop everything from my memory. I'm going to set statistics IO on. I'm going to set my actual execution plan, because what I want to show you is that no matter what we do, when we select from a heap, it's a scan operation. So you can see 100% of this is a table scan. And set statistics IOs let me understand the IOPS operations. If I come over here, let me get a couple of these lines, I can see my logical reads. My logical reads are my memory, but I can see that read ahead reads, I had 2,940 read ahead reads that uses the read ahead mechanism to be able to read 64K pages at a time or 64K extents at a time instead of 8K pages. So now what I'm going to do is I'm going to create a clustered index, and I'm going to create that clustered index on our table that we've named Heap. Kind of ironic, right? And then what we'll do is we're going to come and we're going to do a select star from where my ID equals 10, the exact same query, but this time around, what we're going to find is that we've got an index seek operation. And if you look at this, I have 4 logical reads. I didn't drop clean buffers before, so it did not pick up any reads. But if we look at this as a comparison, again, that should be about 4 reads. But you can see we are reading massively less data to be able to do a seek operation on a clustered index versus a heap. So if we want to look at the internals of this a little bit more, dbcc ind will allow us to be able to look at the individual pages that we have associated with the clustered index. And what we're going to do is I'd like to get an index page type 2 on that level. That's page 8000 right there at the beginning. If I do a dbcc page type 1, I'm going to get the hex output. This gives us the metadata header information. It also would allow us to be able to look at this. You can see, keep in mind the record size for each of these is a row size of 14. And then we've got the value sitting in hex. And now we're going to do a page dbcc page type 3, and we get a friendly output. And look at some of these columns. Specifically, I want you to look at the Uniquifier key column. Our value is unique, but if it was not, it would add an integer value into the Uniquifier. And keep in mind the row byte size is 14. It matches up what we saw on the page. And there's our unique values that we have. You can run out of Uniquifiers. Very, very rare to have that happen, but I have seen that happen. That's going to happen when you have the capability to have a non-unique clustered index. Keep in mind, we didn't put a primary key constraint. We didn't put a unique constraint on this. And so the Uniquifier is put in by default for a clustered index. So if I want to create a non-clustered index, keep in mind there is a size limitation. I tried to do this on a column that's 3000 bytes. And as you can see in the newest version of SQL Server, it's 1,700 bytes. In previous versions, it was 900 bytes. So we've got some extensions. So if I go and I create my non-clustered index on a smaller column, it's going to create just fine. Now, this is just to show you that if I do a specific column seek operation using a non-clustered index, I can also shortcut the logical reads that I need to be able to get an operation to succeed like this. If I were to drop this, then I would have a scan operation. But also you can see I did a select star instead of just asking for that one key value. Now I have a key lookup. Key lookups are low-hanging fruit that we like to get rid of when we're doing performance tuning. Only 9 reads with this. But a key lookup operation is something where it could cause metadata overhead. So I'm using sysindexes to be able to look at the index ID that I have on my table. And I could go and look at that a little bit further. Now we're going to move on to looking at non-clustered index that points to a RID lookup. So I'm going to create another heap table. We're going to call this heap 2. We're going to keep the exact same structure we've had before. Integer value, 3000 byte char 500. So again, we can fit 2 rows per page. I'm going to insert 15,000 rows. And then what I'm going to do is I'm going to create a non-clustered index on this. And I'm going to come down here and I'm going to look at the structure of my non-clustered index. And I'm going to grab page 578 because it was a page type 2 and it was an index level 2. I can look at this and I can look at some of the data that we have associated with it if I wanted to look at the metadata operations, but I'm going to do a friendly dump style. The reason is I want to look at these 2 columns, the key column and the heap RID. So my key columns for my non-clustered index are listed, but there's also this heap RID value, and that's because our table is a heap, not a clustered index. I'm going to grab the page 578. And I'm going to grab this value because we're going to look at this specifically, D1200. And then I also want this RID key, because what we're showing is this is what SQL Server does internally if we have to do a RID lookup, if we're looking at the rest of the table. So we're going to break this hex up, and this hex actually will give us the page ID that we need to look at. It's a pointer. Keep in mind that we're doing this operation internally of SQL Server every time that we want to be able to find this. If we do that select star, if we're getting anything not in that non-clustered index. So if I do a DBCC page, and I'm going to do a friendly lookup on this, and I'm going to do a quick find, and let's find our value, D1200, and there it is. Now, again, we're doing this in dump style 3, which is the friendly, so it translates this hex for us so that we could find this value is 20 as all the white space surrounding it. But there's our D1200 value. Now, keep in mind, that's what SQL Server had to do. It used that D12 value. It used the Uniquifier to find this physical page, to find the rest of the data for the record. So how do I show you that SQL Server is doing that? If we move back to our code, and then what we'll do is we'll do a select my chart2 where value D101. And I'm going to include my actual execution plan. You can see it's an index seek operation. But if I change this to where I'm asking for a value not on my non-clustered index, very quickly I can see it's a RID lookup. And keep in mind that RID lookup can be expensive. Now, if I'm doing this operation once a day, probably not something that I have to performance tune. But if I'm doing this once every, second, or 20 times every second, then I probably want to performance tune this. So what did we cover? We covered quite a bit. One of the things that we talked about was the internals of indexes and the internals of heaps. These are the internals of the data structures and where our data is stored in SQL Server. By understanding these internals, you'll notice by the time we got to the end, I start to talk about performance and how performance is impacted. We talked a little bit about overnight indexing jobs and why we see log growth. We talked about heaps, and we talked about RID lookups. We talked about key lookups. We even unintentionally compared the size of a clustered index 11, with a primary key constraint on an integer value, 11 bytes, to that of an integer value that did not have a unique constraint and required a uniquifier, 14 bytes, which adds size to our index structures, which adds to our intermediate, which adds to our root level size. So we inadvertently, through talking about these internals, start to understand why we get performance overhead with indexes. Well, you know where we like to keep this conversation going? Down in the comments. Was this helpful? Anything you'd like to see? Anything you want to dive into further? We'd love to hear from you. Don't forget to hit that like and subscribe button if this is your first time at Tales from the Field, and we hope to see you again. Thank you very much.
It's gonna be a good day. Wake up. Today's gonna be a good day. So life ain't easy, yo. I think there's a reason though.